We will move to the next one. The next presentation is about the impact and blast resistance behavior of oil palm shell concrete and comparison with normal weight concrete with Dr. Alengaram. Okay. Let's start with the presentation, please.
Yeah. Hello. Good evening, everyone in Kuala Lumpur, Malaysia, and good afternoon, those who are outside. And can you hear me? Chair, conference chair, as a session chair. Can you hear me? Hello. Can you hear me?
Yes, we hear you. We hear you.
Okay.
And we see your presentation very well.
Okay, I would like to thank the organizers. I would see one of the best organized conference, and thank you again. And also I would like to express my gratitude to my previous presenter who has given me more time. So thank you again. I'm going to start something on a new innovative work on oil palm shell concrete. I hope this is the first time in the world that agricultural waste has been used to test for its blast and impact resistance. So you will see that the work that our university or researchers we have put in is really worth maybe exploring. Okay, as per the Elkington in 1998, he mentioned that when we design or when we come to conclusion of any of the structures, we have to have the balance of these three elements. One is people, prosperity, and planet. By balancing these three decisions that we call stool, three legs of a sustainability stool, according to Elkington. So we can get a good result. But today, sometimes we look into the people, but we let down the planet, or we may focus on prosperity, and there will be consequences for other two. So one of the examples we see here, United States consume 30% of the total world's energy and 60% of electricity annually, just for less than 5% of the world population. Also, if you look at the water they use every day, potable water, to flush out the toilets in the US, 5 billion gallons. But that water is enough for the entire world, every person in the world. Because we see, I'm from a country in India, where we see there are many places water scarcity. So we see that one place abundance or use wastage, another place difficulty in getting the basic needs. Okay, look at this, the devastation due to blast. It can be natural or man-made or even otherwise. So if you see that there are a lot of catastrophe due to the blast. So are we having enough resources? Even if you look into the design, if you look into the design, according to the LEED certification, normally they consider energy saving, water efficiency, CO2 emission reduction, improved indoor environmental quality, and stewardship of resources and sensitivity to their impact. These are the metrics they use in the building certification for LEED. So if you do not know what is LEED, it is called, it's an acronym for Leadership in Energy and Environmental Design. In most of the Western countries, in less especially US and Canada, they do use this certification. In Malaysia, they use Green Building Index. So if we see there is nothing to do with the blast or any blast resistant structure here. Probably in future, they may consider certain structures that are subjected to blast or impact resistance. Okay, now let me go to the oil palm shell concrete. It's a biodegradable material available plenty in Indonesia, Malaysia, Nigeria, Ecuador, or some other tropical countries. We developed this oil palm shell concrete. We call lightweight because the density is less than 2,000 kilogram per cubic meter. We studied its mechanical and structural behaviors. Then we went on to test for its blast resistant properties. In Malaysia, millions of hectares, probably 18% of the land under the cultivation of palm oil plantation. You can go everywhere. And these are the information. I don't go through line by line. It's given in the Malaysian Palm Oil Council website. You see, they started in 1870. And today, it's over 5.9 million hectares, or 18% of the total land, as I mentioned. And they produce 19 million tons of palm oil plus 2.2 tons of million tons of palm kernel oil. So if you look into this, that up to 60 feet, the oil palm can grow, and the lifespan about 100 years or even more. But normally they cultivate only for 20, 30 years. They replant it because of the domestic, commercial, economical reasons. So if you look into this fruit bunches, after extracting the palm oil, see, each bunch probably has 1,000 to 3,000 fruitlets, and may weigh 20 to 30, 25 kg, each fruit bunch. And imagine each fruit, about, say, let's say, average 2,000 fruitlets. Each fruit has, say, after extracting, they sterilize first, then extract the palm oil. And this is the squeezing of the fruit. And what you see in the palm of the hand is the palm kernel. That's the kernel. That is encompassing the kernel kernels. That's the shell here. You see, this is shell, and this is the kernel. They extract the kernel to extract another oil called kernel oil. So if you see here, it's very easy. Most of you know, but some of those who come in this meeting may not be aware. This is the kernel. This is the palm fruit, fleshy, that they extract the palm oil, cooking oil. And this is the shell we are talking about. This is called oil palm shell, the brownish in color. They once, 30 years back, when Professor Abang Abdullah from UPM, he's the pioneer in Malaysia, he started this work. And I think I pay respect to Professor Abang Ali of UPM. He's one of the pioneers, and nobody did this work except him in the beginning, 1980s. So when he started this work, it was considered novel. And afterwards, many, including me and my students and others, they have taken up this work on oil palm shell. So we have gone ahead to do something on blast resistance capacity. If you look into this here, we see that the shells have a different shape, convex, concave, and broken surfaces. And we see their thickness varies, depends on the species. And we tried two types of concrete. One is the conventional crushed granite aggregate concrete. Another one, we use the oil palm shell concrete. So two types of concrete we cast using these two materials. You see that they're quite contrasting. If you use the density, if you look at the density, 1,500, here it's half of this. Less than half of this. And the thickness, we can get the crushed granite, any desired size, probably 20 or 40 mm. Here, this is the thickness is the 0.7 to 3 mm. But the sizes means the size can vary up to 12 or 14 mm from 5 mm onwards. This specific gravity is half of this conventional crushed granite, and the finest modulus is quite more or less similar. And whereas the water absorption is 24% here, and the aggregate impact value is almost 4 times this one, normal crushed granite. This has 1/4 of this value. That is what enabled us to investigate its impact resistance. So we did an impact. I'm not showing here much because of the time constraint. And we did this concrete, two types of concrete. Here, only addition here was the silica fume. We wanted to add the silica fume. I tell the reason later on. And this is the mixed design. We as known, because this is by volume, so we can't use by weight, equal weight, because of the specific gravity. And the density of the concrete, if you look at, is 2,300, roughly the normal weight concrete, whereas the oil palm shell concrete, 1,800. So we see that the strength, we get more or less 30 grade, both roughly 30 grade, and the flexural strength was 4, and this 3 MPa, megapascal, whereas this one gives the real attitude or the impact of the oil palm shell. See that similar strength, almost 30, even though slightly higher normal weight, but this one, the lightweight, and you see that the modulus of elasticity is 12 this GPa, whereas this one is 27 GPa. Therefore, this has something to do with, then the strength, as I mentioned, that already I have shown, and there's tiny pores, millions of tiny pores on the surface. and there are undulations you can see seen from the micro SEM, and there are 20 to 30 micrometer the size, the tiny pores. When we used only the cement, it did not get filled up. This one didn't get filled up, only cement particles. So we knew the bond between the matrix and the aggregate. This is the oil palm shell, and this is the convex surface. Millions of tiny pores, they are not filled with the cement matrix. So what happens? The bonding is not that good. So what we did was we added a silica fume particles with a cement 10%. Then we see that after adding this silica fumes 100 times finer than cement, so it could fill most of these the tiny pores with the 30, here 20 micrometer, here 27 micrometer, and so on. Later on, what we did was we went on to do the beam casting. So we did a beam test. This is the structural behavior. We did quite a lot of tests on this, and we noticed this is the normal weight concrete, and it does not have many cracks, because after certain cracks, the cracks widen up. Whereas the lightweight oil palm shell concrete, you can see double the number of cracks. So that enabled us even see that the normal weight concrete, the maximum cracked weight, ultimate load is 0.66. Here it is half of that crack roughly. So even the first crack load quite more or less similar. Therefore, what we understood from this is the total number of cracks in the normal weight concrete only 10 to 12, whereas here it is 2 to 3 times higher than the number of cracks. So that enabled us, that means more the number of cracks, the less the crack width. Therefore, this is some of the information on the deflection. The oil palm shell, the ductility characteristics was found in the deflection. So more the deflection, because the lower stiffness of the OPS enabled low MOE, modulus of elasticity, but has, due to that, it's got higher deflection. At the same time, it has a ductile failure in that. So we see that double the deflection compared to the normal weight concrete. It may sometimes seem, oh, worse. No, it is not the case. Because of the ductility, it can give more warning to the inhabitants. Means it will not collapse drastically like a normal weight concrete. It will give enough warning, and it will not have a, we call it as a brittle failure, rather it is a ductile failure. We see that even the strains in the steel bar, almost 12,000 micro strain compared to 3,000 micro strain in the normal weight concrete beam. So I'm rushing to the last part of my presentation is on the blast and impact resistance. After investigating the mechanical, after investigating the structural behavior, we went on to do the blast and blast resistance. So what we did was we cast the slabs with the reinforcement, appropriate reinforcement. We poured the concrete normal way, then we packed the slabs because we had to send it to Huludo in China with our help of our University Adelaide in Australia, then Melbourne. They helped us to do a test in Huludo, China with the Institute, Beijing Institute of Technology, who handled the blasts. So this is the arrangements that we have done with the standoff distance. You can see here, these are the blast, that we have to keep the blast. Here we can see the standoff distance is only 1.5 meter. This is the slab. So in the slab, we can see that we have to do first 1 kg TNT charge weight. Afterwards, we have to use the same slab with the 10 kg TNT. Then another slab, we have to use directly 5 kg. This is the standard they use for the blast. So the standoff distance being 1.5 meter, whereas the charge weight, we have to do same slab, 2 charge weights, whereas another slab, we have to use the 5 kg TNT. So this is the, we call scaled distance, which is this standoff distance divided by this 1/3 cubic root. So give me a minute. So this is the different setup of the testing. Then after the test, what we noticed is when the blast was ignited, that the charge was ignited, there is a fire, there's a pressure, there's an impact. You see the difference between the normal weight concrete and the lightweight OPS concrete, completely shattered. We can see the steel bar, and we can't go near because you see these shrapnels kill the people. During the blast, there is a fire, there is a pressure, there's an impact. So why do people get killed? Not just the blast as a consequence. One of the consequences is the shrapnel that are created because maybe there's a glass or there are concrete strap pieces that are being thrown out and hit the people. So you look at this one, after the same 10 kg TNT, it was intact. There are a lot of cracks, but it was intact. Why is it? Because of the fibrous nature of the oil palm shell. It could absorb the impact, it could absorb, and it could withstand the blast. Okay, so maybe I can just have this video just for you to show. 2 minutes. I will finish on time. This is the blast, impact, and the fire, 10 kg TNT. This is the effect of the blast. You can see the reinforcements. This is the impact. Maybe I did not share the sound, but you can see that video. Maybe give me, and you see the completely shattering of the slab. But now we see the oil palm shell concrete. Then you see that there are multiple cracks at the base, but it did not get shattered. The same 10 kg TNT. So you can see that. So there are numerous cracks. However, the slab was intact. We can see that the slab was intact. After the 10 kg TNT. There was no crack. There was no wider cracks. There was no shrapnel. Okay, that's about the slabs, and the last one is just to conclude my presentation, because I'm on time. I hope there is enough time for others. Normal concrete panels with the normal weight concrete and oil palm shell concrete were prepared and tested using for quasi static as well as blast loads. We can see here 1 kg, 5 kg, and 10 kg TNT with a standoff distance of 1.5 meter away from the slab. So OPS has a fibrous content, so it was able to absorb the energy. It has the potential as an impact-resistant material. I think this is quite important finding in this research. This is the first time, I believe, in the whole world that there is some research on the effect of oil palm shell, that it can absorb the energy, it can absorb the impact, it can absorb the blast. So 1 kg TNT, the slab was behaving as elastic. And even for the OPSC slab, withstood the impact due to the blast waves and the fireball, and there was no sign of any shrapnels compared to the normal weight concrete, unlike the normal weight concrete slab. Further, despite multiple cracks, OPSC slab was found to be intact even after the 10 kg TNT. It shows a remarkable blast and impact resistance. That this indicates that OPS, that means oil palm shells, are effective alternative for granite or other coarse aggregates, when resisting the blast load. With that, I say thank you, and if there are any questions, I can explain. Okay, thank you very much.